what other structures we can consider in graphs. So we were mainly talking about subgraph relation. So H is a subgraph of G, and we wanted to find a certain subgraph of G, which is again isotropic to certain H. But instead of this subgraph relation, there are other natural substructure of G that we have learned in the undergraduate graph theory. The two of them are the minors and subdivision. So subdivision is subdivision of F is when we start from F, say, let's say your F is K4. What you do is you replace each edge with a path of certain length. Then the result is a subdivision of F. Or we say this is F subdivision. And minor of G is a minor of G. If we start from G, and then we either looking at or multifill or contracting adjacent multifill. And then we do that to obtain H, then we say that H is a minor of G, or G contains the H minor. Both of them are quite topological operation. So topologically, I mean, an H is just the one-dimensional curve, and path is also one-dimensional curve, so there are not really different between them. The subdivision is a natural operation that preserves the topological property of the graph. If contraction is also quite natural property. If you draw your graph on plane, then let's say you draw it this way, then there are, I mean, more than one way to draw it. And you might want to draw in a way that this edge is shorter. You can, instead of draw this in this way, so topologically these two are like indistinguishable. Then you might take this edge shorter and shorter until these two vertex collide and then merge into one. So, I mean, that's also quite natural in this sense. So we can ask questions that, I mean, how many edges in an n vertex graph that guarantees the H minor or H division in G. So it's same with the question for extremal number, but instead of finding subgraph, you now want to find the H minor or H subdivision. So you don't have to find H as a subgraph of G, but you want to find some other graph as a subgraph of G, and those other graphs is H minor or H subdivision. Okay, and for this question, I mean, it's more convenient to talk about it in terms of the average degree than the number of edges. You will see later that this answer is usually linear, some constant times n. And this constant depends on H. So just focusing on this number is more convenient. You can write it without, I mean, using n. So we can define, say, for given f, we can define as the extremal function, the t minor of f, as like we take the limit of n goes to infinity, and then you want to find the infimum c such that if you have a n vertex graph, or I mean at least n vertices, and the average degree, I mean let's say average degree is at least c, imply that B contains F minor. Then, I mean, then you can say that for fixed n, okay, give me a moment. Yeah, so for even fixed n, if you have if you know that your average degree is at least C plus epsilon, then if n is large enough, that it contains F as a minor, and you can consider the same thing for subdivision. Here, this is the average degree. Try to extend the number of edges divided by the number of vertices n. And thinking of these parameters are natural. And first, in 1984, Kostochka and independently by Thomason, they show that in order to get the KT minor, you need the average degree to be t times square root of log t. So they show that if you have more than some large constant times t times square root of t edges, I mean, the average degree is more than that, then it contains a KT minor. In 2021, Thomason further determined this number up to pretty correct constant. And what's this lambda? This lambda is you maximize overall positive alpha, its specific number. Is it roughly 0.638 dot dot dot. And later, Myers and Thomason in 2025 show, I mean, that for general H, they also show that this H yields certain number, which is a correct number, correct constant you have to multiply in front. And this number should be computed, I mean, via some optimization problem. So in general, it's not so easy to, I mean, compute. And in 2000, what did I write here? 2005. And later, Thomason did I write two S's in here? Yeah, Thomason and Wales in 2022 show that this is right. You can actually plug in the square root of the average degree of H in here. And this provides an upper bound. And then this is height for almost all graphs. And these results kind of holds for the graph with polynomially many edges, meaning that almost all graphs with n to the 1 minus epsilon, at least this many edges. And for spiral graph, the correct behavior, the correct constant that's multiplied here is not really well understood, but some sporadic results are known. And in 2022, I mean, the results by Andre, Norin, and Wood and also Eckler-Grave, him, and Dew. So they consider the partial graph, the graph with bounded degree, bounded maximum degree. And I mean, some separability condition. The separability condition basically means that your graph has not so high connectivity in some sense. But anyway, so there are lots of research has been done for finding a minor of certain graph H. And now we want to show that the this complete graph on keyword is this number is almost some constant times t times log t. So meaning that if we have a n vertex graph G with the number of edges being large, let's say like 20 t square root of log t, then G contains kt minor. So we want to show this. And we want to follow proof by Alon, Krivelovich, and Sudakov. This proof is from their paper in 2023. And so roughly what we want to do is if you have a graph G, then you consider, say, G prime by contracting two vertices into one. And if you find the H minor in here, then it's automatically you find the H minor in G. So you can contract edges as much as you want, and then you try to show what you want in that graph. But what we know is that if you have a graph G, and then you can do like deletion of vertices, deletion of edges, and contraction until you get quite dense graph. Why? I mean, if you have a two vertex, and then they don't have many common vertex, then you can shrink it. The number of vertices decrease by 1. And if they don't share any common neighbor, the number of edges also decrease by 1 only. Then average degree goes up. Because per vertex, the number of edges there, per vertex is what? It's large number. So that means you can keep do that, and then you can keep to that while you don't decrease the average degree. Then at the end, you will get the graph where every two vertex has lots of common neighbor. Every two adjacent vertices have a lot of common neighbor. Then what you can do is you take one vertex with a high degree, and then you focus on this neighborhood, induce subgraph on this neighborhood. And every vertex here, what? This two has lots of common neighbor means that this vertex has lots high minimum degree in here. So we can reduce our situation into dense graph. And in dense graph, what do we have to find? We want to find the, say, many set. D1, D2, D3, D4, so that these are connected. And then there are at least one edge between them. Okay. And once we know four such things, then next thing you want to do is you find the P5 so that this is connected, and then it sends at least one edge, one edge, one edge. Let's say you take A1, A2, A3, A4 small set, such that every vertex outside AI has a neighbor in BI. Then, as long as your new set P5, if this entirely belongs to one of AI, then there are no edges. But as long as this does not entirely lie inside of AI, if it contains at least one vertex outside of AI, then you get edging. So that's roughly how we want to show. We connect set one by one. And then while you're doing that, we find the small set AI such that this is adjacent to everything effective. And then you find the new AP5, which is connected, and then which is adjacent to pretty much everything except very small set A5. And then this does not entirely contained in any one of them. And then we will repeat it until we get the KT minor. With that plan on our mind, we prove the following lemma. So consider an n vertex graph H with the minimum degree at least n over 6. And let's say you have sets A1 to AS vertex set, and each of AI has small size n times e to the negative 1/3 square root of log n. That's for log n. For all I. And and let's say the number of such states is m mod n over square root of log n. Then what we want to show, this is the situation here, and then we want to show that we can find the new set B. Then there exists set B of size say at most 3.1 times square root of log n, such that the neighborhood has size at least 1 minus e to the negative square root of log n divided by 3 times n. So it's adjacent to pretty much everything except very small fraction, and then that small fraction at the size of AI, and B minus AI is non-empty for all I. And ideally we want to make it connected, but we can actually make it pretty close to being connected. It has at most 6 components. So let's prove this. The proof is more or less standard probabilistic method. So let P be the probability that we want to, not probability, be the size of B that we want to choose. Let's say this is 3.1 times square root of n, and we choose vertices B1, B2, BP from the vertex set of H independently at random with repetition. So it's okay that the same vertex can be B1 and B2 at the same time. Let's say B be the chosen vertices. Then what happened? For each vertex in there, we can compute the probability that this neighborhood has so this is the probability that this B is not in the neighborhood of B. So this is a probability. So if none of the neighbor of B is contained in B, then that's the bad event. But when will this happen? This is at most 1 minus the degree of B divided by n to the P. So its choice is independent. So this is what? This is at most e to the negative degree of B times P divided by n. And we know that the minimum degree is at least n over 6. So this is at most e to the negative P over 6. Thus from that, the expected size of the vertex is not covered by another neighborhood in B is at most n times e to the minus P over 6. That's like n to the smaller than n to the e to the negative half square root of log n. So this is small. And what? Using Markov inequality, that this cannot be, it's unlikely to be much bigger than the expected number. So this is quite small number, so we make it a bit larger. And this holds with probability, say at least 0.99. Assuming n is large, let's say. Okay. Also, that's regarding this event. And there are this event as well. Also, for each I, what's the probability that this B is entirely in A? That's also you can calculate. The one vertex in there with this probability, and then you have to take the power, piece power, and what this is e to the p is like 3.1 log n divided by, wait, what was the size of A? Size of A was yeah, negative 1/3 square root of log n p, and this cancels out, e to the negative 1/3 square root of log n divided by p. Give me a moment. What am I saying? To the p. So that's e to the negative 3.1/3 times square root of log n times square root of n log n. Yeah. So that's more than 1/n. Thus, the union bound implies that, so if not contained in AI, or all of them, with probability at least 1 minus f over n, which is at least 1 minus 1 over square root of log n. So very close to 1. And finally, we want to make sure that it has a most 6 component. For that, what? Let's say we condition on the choice of Pi. As all the choice of B1, B2, B3, those are independent. Once we condition on that, the number of neighbors of this in B is like, we consider all the other Bj choices of Bj with j not equal to I. There are P minus 1 of them. And so we get that the expectation is this. And we know that this is at least n over 6. So this is at least like p over 6 minus 1. So using Chernoff bounds, the probability that this is smaller than p over 7 is at most e to the negative. So you compute the difference, that's p over 42, and then you take the square and then you divide by 2 times p, and you do the computation, then it's at most, say, negative p to the 10 to the 4. And hence we assume n is large, and then p was what? This. So you can actually show that this is m mod 100p, 1 over 100p. And again, the union bound. This vi has at least more than like p over 7 neighbors for all I with probability at least 0.99. So this probability, this event, this event, this event, as the bad event happens with less than probability 0.01, then there are 3 types. So the probability that at least one bad thing happened is at most probability 0.03. So that means with positive probability, none of the bad events happen. So thus there exists a choice of B such that all the good things happen. Meaning that this has in degree bigger than p over 7, and AI b minus AI is not antiset for any AI. And out of here, the non-neighbor has very smaller size. Sorry, that was my phone. Anyway, if that happens, this has minimum degree at most at least p over 7, meaning that it has at most 6 components. If there is 7 components and one of them, the vertices in here has degree smaller than p over 7 because it has p vertices, less than p vertices. So all the things have been proved for this lemma. So this lemma is proved. And then now with this lemma on our hand, we can prove what we want. The statement that we want to prove. Yeah, okay, perhaps it's good to break the video here. And then we talk about the proof in the next video.